Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to subscribe and share my videos to your friends and to your friends' friends. That's the only way you can help me promote my channel and to keep me going, refreshed, and inspired. And I'm very willing to share my knowledge, especially topics in civil engineering for your benefit. The pipe carrying steam at 3.5 megapascals and an outer diameter of 450 millimeters and a wall thickness of 10 mm. A gasket is inserted between the flange at one end of the pipe and a flat plate is used to cap the end. How many 40 millimeter diameter bolts must be used to hold the cap on if the allowable stress in the bolts is 80 megapascals, of which 55 megapascals is the initial stress? What circumferential stress is developed in the pipe? So for part A, here is the figure. This end cap here will be subjected to internal pressure times internal area, and it will be resisted by the stress in the bolts. The remaining stress in the bolts, because it is subjected to an initial stress of 55 megapascals, would be allowable minus 55, then times the area of the bolt times the number of bolts. So that's the total force that will resist the force due to pressure at the end cap. So that's pressure times pi internal diameter square for that force that pushes this end plate. Then it will be resisted by the tensile strength of the by the available force in the bolt, which is number of bolts times force in one bolt. And the force in one bolt is the allowable stress in the bolt minus 55, because it has an initial stress of 55 megapascal. So the allowable stress which will resist this force here would be 80 minus 55. So summation forces horizontal equals 0, N times FB equals pressure pi Ri square, where Ri is outer diameter over 2 minus thickness. So 450 divided by 2, outer radius minus thickness, 215 mm. So substitute FB is allowable stress minus 55 times area of 1 bolt, which is pi 20 square. The radius is 20 mm. So N times quantity 80 minus 55 times pi 20 square equals pressure 3.5 megapascals pi Ri square. So that N is equal to 16.7, 16.18. So use 17 pieces of 40 mm diameter bolts. So 17 pieces of 40 millimeter diameter bolts. Circumferential stress is PRI over T. So circumferential stress is pressure R sub I over T. So substitute pressure equals 3.5 Ri 215 over thickness 10. So the circumferential stress is equal to 75.25 megapascals. The ends of the 75 millimeter inner diameter bronze tube are attached to rigid walls. Determine the longitudinal and circumferential stresses when the tube is pressurized to 2.75 megapascals. Use modulus of elasticity of 82.7 gigapascals and Poisson's ratio of 1/3 for bronze. Neglect localized bending at the ends of the tube. So looking at the figure, because the walls are rigid, so longitudinally, strain is prevented longitudinally, but circumferentially, it's not. So therefore, sigma sub c, which is PRI over PDI over 2T, is also PRI over T. So it is not prevented, so we use this formula here. So the inner diameter is 75, so the inner radius is 37.5 divided by 2.5, that's definitely more than 10. I think it's 15, so we can make use of this formula, not the average value for di or diameter. So sigma sub c is pressure, 2.75 megapascals times 75 over 2 times 2.5. So it is equal to 41.25 megapascals. So the longitudinal strain should be 0 because it is prevented in that direction because the walls are rigid. So strain longitudinally is 1 over A quantity stress longitudinally minus Poisson's ratio times stress perpendicular to longitudinal direction. So that should be the strain, that should be the stress in the circumferential direction. So that it is equal to 0 because there should be no strain to develop longitudinally because the walls are rigid. So therefore, sigma L equals Poisson's ratio times sigma sub c. So stress longitudinally equals Poisson's ratio times stress circumferentially. So longitudinal stress is one third of 41.25. So longitudinal stress is equal to 13.75 megapascals.